Okay, thank you very much. Hello, everyone, and thank you for this opportunity. It's a great pleasure for me to present here our research. And today I present my joint research with Professor Petrosyan, Cooperative Differential Games on Networks. So first I give a brief overview, the history of this problem, and then our fresh result in this topic. Yes. First, this problem was considered in 2010 by Professor Petrosyan. He introduced the cooperative differential games of networks. It was an in-person games where players were connected in the network, and the main assumption was that in any instant of time, players can cut connection with the players that connected with them by an edge in the network. Say we say that such set of players for player I is K of I, and every player I can cut connections with every player from the set Ki. Also, it is important that motion of players are independent. Equation 1 gives us the view of such motion equations, and equation 2 gives us the payoff of player I. We can see here that player I has the payoff that he can get by itself, and also he can get something from interaction with other players. And we can see that he can interact only with players that are connected with him by an edge in the network. Also, we assume that these pairs that he gets through the interaction are non-negative. So it was shown then in such games, when we consider about cooperative game, it is easy to compute the characteristic function, because unlike the classical way of construction the characteristic function, here we can don't consider the operation of minimization of players from anti-collision n minus s, because the worst thing they can do for the players in collision s is to cut the connection with the player from s. So if they cut the connections, then as the worth of collision s is just the sum of pairs that players get through the interaction, which is other in this collision. So we consider only players from the set Ki in this collision S. And of course, it is easier to compute. Oh, I'm sorry. In opposite direction. Sorry. Now. Yes, and also as the next step in this problem was done in 2020 by Professors Petrosyan and Young, and here, as can we see, also the operation of maximum is absent too, because they introduce characteristic function on the cooperative trajectory and cooperative strategies of the players. So here we just need to solve only one optimal control problem to find optimal cooperative strategy and optimal cooperative trajectory, and then it is easy for us to compute the characteristic function of every collision S. And of course, it is easier to compute such characteristic function, and also there are some good properties of such characteristic function. It was shown that this characteristic function is convex. Now we are considered we continue to consider this problem, and for the same problem statement, we also find the view of the Shapley value, the explicit form of this solution, and as we can see here, we need now to compute the characteristic function at all. Again, we just find the cooperative trajectory and cooperative strategies, and then we need to divide the pairs that players can get through the interaction with each other in equal parts between these players. And it gives us the Shapley value in this game. We consider such an example where we have a linear quadratic problem, and it is interesting for us was to compare the classic characteristic function and the new view of characteristic function for this problem. We consider the game on such network with 4 players, and this is the graph that gives us the comparing of solutions. So here the bigger figure present a new characteristic function, and it is the core. It is the core of the game, which was constructed with the use of new characteristic function. And the smaller figure gives us the core of cooperative game, and this core was constructed with the use of classical characteristic function. So we can see the difference between two solutions, and also here we can find the Shapley values in two cases. This blue point is the Shapley value with new characteristic function, and green one is the Shapley value with classical characteristic function. Then we consider another problem statement when we assume that players can interact not only with which players that connected with him by H, but also we assume that interaction is possible if players are connected by paths in the graph, in the network. So here is the view of pair of players. Again, we assume that the motion are independent, and let's understand this part of the pair. So Km of I is the players that are on the distance of M in the network from player I. Here also we have multiplied delta in the degree M minus 1, because we assume that this multiplier shows that the further players are in the network from player I, the less their behavior influence on the pair of this player. And also here we have new letter R. It is the restriction for our communication. So we assume that if the distance between players is more than r, then players cannot to interact with each other. Again, we assume that players cut connection in any point in the game, and again we assume that the pairs are that players get through the interaction with other players are non-negative. The characteristic function is introduced in the same way as was proposed by Professor Petrosyan and Young. So again, we consider the characteristic function on cooperative trajectory. Again, we have now here the operation of maximum and minimum. We just calculated on the cooperative strategies and trajectory. And to simplify our view of characteristic function, we make some denotions here. By this denotion, we denote the sum of pairs of players that they get through the interaction with each other. And it is the pair that player I can get through that interaction with player G. And here the pair, the instantaneous pair, that player I can get by itself. So we write the characteristic function in such way. And we prove that if we construct characteristic functions in such way, and if there are no cycles of length less than 2r plus 1 in the network, then such characteristic function is convex too, as in previous problem. Why we need such assumption about the cycles in the game? If we have the cycles with the length less than this number, then it is possible that the players have two different passes with the same length between them. And in this way, the convexity of characteristic function can be broken because players can go from one path between them to the interaction through the other path between them. So we give here we put here such a restriction, and we need to say also that if we consider the game without cycles, the network without cycles, then the characteristic function is also convex, and also we can consider the interaction without restriction of the length of the path. So we, in this case, if we have no cycles at all, we can put here n-1 and say that players can interact if they are connected by any path in the network. But as we say about the dynamic game, the important property, of course, is the consistency of cooperative solution. And if we consider some optimality principles with the set of imputation, then such situation is possible when the players in some moment of the game decide to deviate from the initial imputation that was chosen in initial point of the game to another imputation from the cooperative solution. And it is interesting if the resulting pair of the resulting imputation of players in the game will again belong to the initial cooperative solution. And it is true.
May I interrupt? I have a question. I'm a bit lost. You started by presenting a framework where you have a case where each player can be connected only to neighbors, right?
Yes, yes.
And okay, in this case, what you said is that it's sufficient to compute the optimal trajectory, and after that, the characteristic function for any coalition S is obtained simply by summing for the players who are in S, one payoff that is coming from the cooperative trajectory, and you have after that an intersection between S and K of I.
Yes.
Okay, so this was the start. After that, when you introduce this delta M, so here the idea that a player can cooperate with any other player in the network and not necessarily with a neighbor.
Yes.
Now, if one player wants to cooperate with another player who is located somewhere else on the network, and you need to go through a path, is it the case that all players along the path must be part of the same coalition or not?
Yes, I forgot to say about it. Here we consider only such paths that are all players lying on this path have to be in coalition S, of course.
Okay, so you need to have everyone cooperating along this this particular path.
Yes.
And okay, and still in this case, you can get the characteristic function by saying that there is one part that is completely decoupled from the network topology by having the summation over S of this integral from T0 to capital T H bar I, and you have one part that is coming from this cooperation. This always the thinking here, because the only thing that can happen that if a player wants to deviate from the coalition, she will cut the link and nothing will happen. I mean, the coalition will shrink, and you can still get the payoff from the remaining players in the coalition, plus the part that you can get from the optimal solution. So this is the way you are thinking about this problem here. Am I right?
Yes. If some players from the path between players are not at coalition S, then this term is eliminated from the payoff, and here we consider only such paths that are
okay.
in
Okay, I see. And there is no cost for building a link or cutting a link?
No, no.
Okay, okay, I got it. Thank you.
And we say now about the consistency, and I say that we are interested in the such property as strong consistency. So here we denote SE the all imputations in the game, and C is the core in the game. And to introduce the next result, let's make some denotions again. So consider a pair PQ in our network. It is the vertices PQ, and assume that the length between this pair is L. So for this pair of vertices, we need to set a vector with the length L such that the sum of its element is 1 and each of them is from 0 to 1. And the set of all such vectors we denote as phi of PQ. And it was shown that in the class of games under consideration, an imputation belongs to the core if and only if it can be represented in the following form. So here we can see such coefficients, and new notion for us, the set dm of I, it is the set of such pairs PQ that player I belongs to the path from P to Q, and the length of path between P and Q equals to M. So we can see that imputation from the core is constructed in the following way. It is the pair that player can get by itself. And here we see that from every path where player I is intermediate or is endpoint, from every such path, player I will get some part of the pair between players P and Q. In this in such situation, this player will be this imputation belongs to the core. So every pair that players P and Q get from the interaction with each other have to be divided from the players, only from the players, from the trajectory from the path between P and Q. And now return to the problem of the consistency. And we use for this the imputation distribution procedure. It's such vectors that we can represent imputation in such way. And we say that optimality principle M is strong time consistent if it is not empty in every point of the game, and also if there exists some imputation distribution procedure that if we in some intermediate point T in the game choose any imputation from this optimality principle, then the sum of the imputation in this subgame and the part that was accumulated to the moment T, according to this imputation distribution procedure, this resulting imputation will belong to the initial optimality principle in the initial moment of the game. So we can choose here any imputation, and again, the resulting imputation will be in the optimality principle M. It is strong time consistency of optimality principle, and it was shown that in our game, the core is strong time consistent. Also, as in the problem when players are communicated only with neighbors in the network, also here we constructed the similar formula for Shapley value, but here the players need to divide equally of the pair that players P and Q get through the interaction with each other between all players from the path between P and Q. So for in the previous problem, it was divided by 2, between two players, and here we need to divide it equally between all players of the pass. So player I will get his payoff that he can get by itself, and also he will get a part from the pairs of vertices P and Q such that player R belongs to the path between them. It is the Shapley value of this problem. Another solution, of course, Shapley value is in the core, and here we can see that the coefficient that was discussed earlier for the core, from the imputation from the core, this coefficient here it is 1 divided by m plus 1. The next solution from the core that was considered is the position value. Position value was proposed by Mearson in 1988, and to construct this solution, the dual game is considered, the dual game between links. So now we assume that players are not vertices as earlier, players are links in our game. And if we consider players as links, then the characteristic function we construct in the same way on the optimal trajectory, but here it has such view, and also we can calculate the Shapley value. So we consider the game between links, and we can see here that the pair that players P and Q get through the interaction which is other now is divided equally between m players, because now there are n players on this path between them. And after we calculate the value of each pair of each link in the network, we can calculate the position value. The position value assumes that this pair of each link divide equally between endpoint of this link. So we get the position value in this game in such form. And if we return to our previous terms, we get it by formula 23. So we can see here that if player I is an endpoint on the path PQ, then from this value he will get such part. And if player I is intermediate player on this path, he will get such part of this value. And to compare the Shapley value and the position value in this game, let's consider this picture. Here we have the game of 6 players, and now we are interested in the pair of players 2 and 4. If we consider the path between players 2 and 4, according to the Shapley value, we need to divide equally the payoff that 2 and 4 get through the interaction which is other. So each player on this path will get a such value from this payoff. And if we consider the position value for this game, we can see the endpoint get only such part, and the intermediate played, the pair of intermediate players are greater than the endpoint. We can give such interpretation here that player 3 have the opportunity to break 2 links on this path. So his power is greater here than the power of endpoints. And on the Shapley value here consider it just the opportunity to break. Every player here can to break, so the payoff divided equally. We also consider here example, and it is interesting in this example for us was to illustrate the strong time consistency of the core. It was such game with linear equations of motion and with not linear equation, payoff equation, and here it is easier to calculate in explicit form characteristic function and to construct the solutions from the core, Shapley value and position value. We need to get some such system of coefficients for every path between pair of vertices. We need to get such coefficients, such vectors. Here we assume that I is equal to, so we consider only the interaction between neighbors and players connected through the path of the length 2. So between the neighbors, we need to get the pair, how to divide players between each other. And if, for example, we consider the path between 1 and 3, we need 3 numbers, how to divide it, the payoff from this interaction 1 and 3 between players 1, 2, and 3. And for example, consider player 1. For player 1, we have 2 players that are neighbors, so 2 such terms in his payoff. And also we have 3 paths that when he is an intermediate player, so not intermediate, when the length of the path equals to 3, or 1, 3, 1, 5, and 1 path when he is intermediate, 2, 6. Here we multiply by delta, and again we need to define these coefficients to divide. So as we consider the Shapley value, every path of the length 1 corresponds to the such vectors when we divide equally between 2 players, and every path with the length 3 correspond to such vectors. When we consider the position value, the same as in Shapley value is for path of the length 1, and when we consider the path of the length 3, here we need to use such vectors. So here, for some value of coefficients, we find the solution. And what is interesting to illustrate the strong time consistency, we assume that to the moment 50 players use the Shapley value, and then they use the position value. So the resulting imputation we get in such form, and then we can understand that this resultant imputation corresponds to such coefficients in the initial game if we want to represent it as the imputation from the core. So we again get the imputation from the core, and if we say that it has to be presented in such form as in theorem, then we find such coefficients, and indeed we see that it is imputation from the core. Yes, we can find these coefficients. And another one solution was considered as the imputation from the core. It's the average tree solution. But now we assume that the network is cycle-free, because the solution was introduced by cycle-free games. As I said already, if we consider cycle-free networks, we can consider here any path of any length. So we put here n-1, and the view of characteristic function is the same as in previous case. Now we will give the definition of the average tree solution, which was proposed here. So we assume that CL is the collection of components of network, and we consider one of such component, and player I belongs to this component. So for each player I, we will consider unique tree Ti. When I is the root, I will be the root, and all direction will be from player I to the endpoints. In such way will be direction, and it will be the tree Ti. In this tree Ti, we will find such sets. The first set is introduced here by red points. It is the subordinates of player G in this tree Ti together with the player G itself. So it is such subset. And also we consider the subset PT. Here we consider players that are successors of player G in tree Ti. 3 red points represents here this set. And consider such values Tij. Here we see the value of characteristic function of subset St. So of this coalition minus the sum of the values of characteristic function of such coalitions. So it is one such coalition from one red point, the second one, and the third one. So when we determine such values Tij, we are ready to give the definition of the average tree solution. On the class of cycle-free graph games, the average tree solutions is a vector given by the following rule. So on the component K, we consider all trees Ti for and for every such tree Ti, we find value Tij for player G and find the average value for this player in this component. It is the average tree solution. In our game, when we consider the interaction of players through the paths, let's understand how we can construct this imputation. As we already said, the characteristic function in such game is convex, and it is known that in convex game, the average tree solution belongs to the core. So we understand that this imputation is from the core, and it's already known for us the form of such imputation from the core. So we need only to determine the coefficients phi, how many each of player will get from the value of the payoff that players get from the interaction with each other if player lie on this path. When we understand how to find such coefficient, it will be clear for us how to construct the average tree solution in this game. So here, consider the path from P to Q and consider player I. We will construct such set Q, K, P, Q of I. It is red subset. And we can construct it by broken H that connect player I with other players in this path. For every player on this path, we can construct such subgraph, and then we get the formula from for the average tree solution. Here we see the coefficients for the payoff from the core in such way. Let's consider it on this example. So we see that in this component we have 12 vertices. So this value is 12. And now we need to find for every vertex on the path from P to Q this value. For player I, we already find this subgraph, and we see that here we have 5 vertices. So he will get such part from the pair of HPQ. This vertices induces such subgraph, and we have here 4 vertices, and it is his part. Only 1 for the vertex P and 2 for the vertex Q. So it is the way how we divide the payoff between P and Q according to the average tree solution. And to compare it with Shapley value and position value, I put here these coefficients for Shapley value, we divide it equally, and for position value in such way. Again, we consider here an example. I guess I have no time already, yes? Right? Or not?
You can still use 7 minutes if you want.
Oh, okay. So again, here we consider example, and let's I think we can just to discuss how to construct the average tree solution in this game. For example, if we consider player 1, we need to consider passes from 1, 2, 1, 3, 1, 4, and also 2, 3, 3, 4, 2, 4. If we consider 1, 2, the pass 1, 2, we need to construct such subset. So if player I cut this link, then we have here in this subset 3 vertices, and that means that player 1 will get such part from the interaction of players 1 and 2. The same will be through the interaction 1, 3 and 1, 4. We find these coefficients in such way. When we say about the paths of the length 2, in this case, player I can cut this link and this link, so we need to consider such subgraph. Here we have 2 vertices, and the value will be 2 divided by 4, so a half. And it will be the same value for all paths of length in this graph for the passes 3, 4 and 2, 4. So we compute the imputation for player 1 and for other players in the same way. And again, we can compare it with the Shapley value in this game. We can see that player 1 can get more according to the average resolution in this game. Here we see a different coefficient, yes, and we see that the Shapley value for player I gives the smaller number. And for other players, unlike the first one, we see that Shapley value gives the more number than average resolution. And we see that the position value and the average resolution, these imputations take in account the structure of the network, but the Shapley value always divide the payoff of players on trajectory equally. So that's all I want to say. Thank you for your attention. Here's some literature. I will be glad to answer questions.